Mhm.
It's my pleasure to introduce Sherry Wu. Sherry Wu is an assistant professor in the Human-Computer Interaction Institute at CMU. Her research lies at the intersection of human-computer interaction and natural language processing, and primarily focuses on how humans, AI experts, lay users, and domain experts can practically interact with AI systems, including debugging, auditing, and collaborating with them. To this end, he has worked on assessing NLP model supporting human in the loop, NLP model debugging and correction, as well as facilitating human AI collaboration. Received her PhD in computer science and engineering from University of Washington, where she was advised by Jeffrey Here and Don Will. She has authored award-winning papers in top-tier NLP and HCI conferences and journals such as ACL, and TOCHI. Please join me in welcoming Sherry Wu.
Thank you, everyone. Should I get started?
Yes, please.
Cool, cool. Thank you, everyone, for having me here, especially for still coming to this talk, despite the faculty interview talk. I feel like those talks, like I was telling Jake, I feel like those talks are the best talks you can give throughout your career. So definitely worth listening. But today I'm gonna talk about some work that we're doing these days about like making AI systems work for imperfect humans. And I'll explain what I mean by imperfect humans later, but I wanted to get started by talking about like a human AI collaboration work project that's inspired or driven by my own pain of trying to do teaching. So last semester, I was tasked to teach like a required course called Data Science for Product Management. And it's designed to have some data science assignments that require students to do some Python coding and like, across different data science procedures. And it sounds really standard, but then I was told that this has been historically a really difficult course to teach because we have a bunch of students who are required to take this course, but they come from really, really different backgrounds. So some of them would come from a technical background, come from STEM, and they have definitely no problem doing coding, but they don't really know much about data and also probably don't know much about how do you actually need data science for product management. They don't know much about the domain. And then I also have students who knows nothing of coding, but they actually have been in the product management job for a really long time. And as a result, they know a lot of the domain. They just really want to be able to read the data more firsthand, do not depend on their data scientist on the team. Um, and the problem is, as a result, our assignment are either too easy or too difficult, because some of the students will be like, "Oh, I don't know Python. How can I even do the assignment?" And also, there will be some questions from the students that even instructors like me won't be able to answer, especially if it's more tied to the domain, because maybe I have never worked in a financial domain before, but they have. So I couldn't really provide all the answers that they want. And so when I learned all of this, I was like, oh no, what should I do? But fortunately, when I took over this class, AI coding, AI pair programmer, AI assistant is already a thing. So I thought, hey, can we just make everyone's life easier by just having them to go and ask large models? And on first glance, it should seem like a really perfect setup that really should help them close the gap because so Google already has Gemini embedded in Colab at that time, and students were required to basically use Colab to complete all of their assignments. And there are a lot of functionalities in Colab just natively without needing any setup. You can have a sidebar where you can ask like general conceptual questions, just like in any kind of AI chatbot. But it also has this like little natural language programming kind of cells where you can wipe code the procedures you want to do for your data science assignment. So practically, you don't really need to write too much code if you really nailed at having AI do all the work for you. And because you can ask questions and you can also just do web coding, it's really offering, we thought it's offering like unlimited possibility of AI usage, and it should be able to give everyone the support that they actually need and help us really close this kind of weird expertise gap. And we had high hope, but probably you could guess. Like eventually, it didn't turn out to be as ideal, and it didn't really close the gap. Only some of the students were able to get the benefit that they really need. So we did some analysis on the students' interactions with AI to really understand when they use Gemini to do what and why some people succeeded and some people failed. And I won't go to the details of the analysis. I'll come back to this slightly later in the talk. But TLDR is we see that like students' own ability to really ask for the right thing in the right way really becomes the key. And good students were able to evolve their task with the AI. So we had some novice students who are just really lost. They do not really know what they're asking the model to do. They're really confused when large model try to explain something back to them, and when the model try to ask them a clarification question because they're so lost, they don't know what to do. They will answer, "I don't know, maybe," and then large model cannot really handle, "I don't know, maybe." And I'll give you an example. So this is in data science, they were using pandas and they were playing with their data sheet and they wanted to do some data cleaning. And one arrow they ran into was this key arrow that says like you're using a wrong column name. This column name does not exist in your data frame in pandas. And this model actually, Gemini has already explained everything. It says like, oh, if the column name is different in the CSV, if the actual column name is something else, you should really change it to something else. But because this is a chat window, the model actually do not directly have access to what's going on in the Colab interface. So it does not really have access to the data column. So it's just giving a hypothetical example of what you should do if you know what your column name is. And students basically said, I have tried this option you provided and I wasn't able to resolve the issue. And it's really not because the model like was not clear or something. It's really just they simply copy pasted this code block and ignored the fact that that Gemini was simply trying to explain that if your column name is total player, what you should be doing instead of saying like your column name is definitely total players. So students just get confused. And I also confused my PhD student. They were like, oh, it's so clear. Like, why would you not be able to follow this kind of instruction? But then there are also other students that actually are like at similar level of expertise. They also don't know much about coding, but maybe they are really just persistent and also they like have this ability to progressively build up their task together with AI. So here they wanted to do exploratory data analysis, and they first wanted to have like a bar chart doing some comparison on this is a game data set that's like comparing genre to like release date. And they realized the first figure generated by Gemini, a pie chart, is too noisy. So they were like, can we filter it down to maybe just top end games so you don't have that many pies in your pie chart? And after several back and forth, filtering things down, they realized, oh, pie chart is actually just not the answer. They weren't sure, like, what are the right visualization? And they were okay with not knowing. And they asked the model, what would you recommend for comparing this to total players by year, whatever their analysis goal is? And eventually they were able to do something called grouped bar chart, which is not something that the student even know before. But they were able to produce it because they know when to ask conceptual questions to a model to handle their own unknown unknowns and also apply that conceptual answer back to their particular task. So key takeaway here is really like they're given the same model and there are people who start with similar level of expertise. And what really mattered here was their interaction style. A lot of times when we train models, we kind of expect there are certain kind of interaction paradigm that any kind of human will be able to just simply be able to master. Like for example, if we do instruction following, we're expecting, oh, people will always be able to write really clear instructions. When we train model to ask us clarification questions, we're saying, oh, we really expect human will always be able to answer clarification questions. But in reality, what we saw is really people are not perfect and not oracle and also not static. Through interaction, they're trying to learn something. And with learning, maybe they will do better. At the beginning, they know nothing. Model are supposed to explain a lot more. And how they do things and how AI react to, really change their task endpoint. And in this case, it was their grade. And generalizing from this observation, one thing I feel like really ground a lot of our work these days is this assumption, this observation that maybe when we build state-of-the-art AI, we're making a lot of assumptions that's basically thinking humans would be perfect. We would have fixed goals and we would be able to have that goal in a really constrained domain. We will be able to explain that goal upfront. We have complete knowledge, we know everything about our goal, and we know when like our goal is satisfied, and that's great. Like people won't have half satisfaction. Everything is either correct or incorrect. But most of the real world scenarios really just involve really imperfect humans, like in learning. They have dynamic goals. They don't know what they're actually trying to achieve in the end. They have a domain that they haven't learned much about. They have a lot of unknowns in that domain. They don't even know they don't know that. And like task completion for them is also a continuous skill. If you reach the end, you get 100 points, but if you reach half, you get 60. So like there's 1 point maybe you've done enough, but that's still not perfect. And how do you even measure that continuity? And it's not just learning. In most of the cases, if you're doing decision making, if you're doing some kind of sense making, if you're doing design, most of those cases you run into this. Like if you want to go for a trip at some particular country or whatever, if you know nothing about that country, you won't be able to judge if a travel itinerary is good or not. You have to first learn about local cuisines, about places you want to visit, about how much money people tend to spend in general in those locations, in order to like really make a decision. And also, it doesn't just apply to novices. Interaction also matter even for experts. This is another example we saw actually in like also doing data science tasks, but like with experts. And this also represents maybe status quo how AI agents are trying to help us. Say like an expert says like I'm planning to open a coffee shop in Seattle and would like to make an informed decision on this investment using the data. And at this point, usually you will have AI agents giving you a high level plan saying like, I will start with data loading, doing EDA, blah, blah, blah. And you would approve, or expert would approve that plan. And you will wait for the agent to do things for 10 minutes, 5 minutes, and eventually will come back with a really, really long, maybe report with many visualization and probably even a lot of line of code trying to show the process of how they did it and what's the final result. At that point, it's like cognitively overwhelming. If there's something wrong in this process, you won't be able to really say, oh, I want to restart from here, or like you won't really have the time or energy to read everything and judge if something is correct or incorrect. So even though a lot of times we definitely want a final output that is really insightful, a more helpful approach to the expert would be maybe the agent will practically pause and first give some initial analysis and ask, oh, do you feel like this is correct? Are there some other things you want to clarify? How is this data collected that might impact how additional analysis should be conducted? What statistical methods should be used? And this interaction process will be able to provide users domain and also data knowledge to make subsequent analysis decisions. So what we think exactly we're expecting AI to do if we are actually facing this imperfect user kind of scenario, which is kind of everywhere. Two things we think are really important to consider. First, task completion probably shouldn't be the sole purpose, especially if you don't have a really clear goal at the beginning. There are a lot of more intermediate goals, like can you articulate this final task much better through the interaction? Can you think about if it's teaching students something, what are some learning gains? What are some other like side effects or utilities that should be considered? And also many tasks just naturally need interaction process because either like human efforts is absolutely needed to improve agent output, or for a lot of knowledge work that are by nature iterative and dynamic, human engagement is really part of that goal. And with that in mind, we want to ask, can we assess and also plan interactions in a way that would make AI really practically useful in complex scenarios when we cannot assume oracle or static humans? And that's basically what our lab tried to do. And it's like a very interdisciplinary question, which is why we also have a lot of interdisciplinary students. We also try to publish across different kind of domains with like within HCI, NLP, and also some learning science domains. And in this talk, I will give you hopefully like a broad overview of how we are trying to make some contribution to this question from different angles. First thing I want to really talk about is how to really think about interaction process if we care about interaction. And for that, I want to talk about a paper called Collaborators Not Equal to Collaboration, Scaling Collaborative Effort with Agents. And essentially, this paper, we want to introduce a framework on explicating the human AI interaction trajectories. So first, let's think about if we do interaction, what might the process actually look like? We mentioned this before, but a lot of times, maybe right now, we would have end-to-end interaction with an agent where a human would give an instruction and agent will just do the job. And the utility that we consider of like the agent doing a good job is really the final output quality is really high, like if fulfill the original instruction. If we consider this more multi-step, if we envision it to become multi-step, we can think about this process among two dimensions, one human effort and two utility, and put it into like an axis. More tasks that would really need interactions would hopefully look like if human put in more effort, you would get better output out of the model. That's like the ideal. And here, the utility probably can be more broadly explained, like the output quality count. Maybe at each step, are you helping people to understand the task more? Are you helping people to learn something? Would also be counted. Unfortunately, in reality, many of the interactions are really just futile. Humans are putting in a lot more effort, but without being able to actually increase the actual utility or like gain from the model. And this is one example from a paper that's like called collaborative theme. Basically, they had simulated users have chat with AI agents collaboratively to complete some tasks. And this is again a data science task. And the problem here is again a column name problem. And basically the human explained this error once and agent took a bunch of different actions and came back still not fixing that error. And human would be like, what can I do now? They basically paraphrased this error and expressed it in a slightly different wording format, but basically it's the same thing. And agent go back and still wasn't able to really do the task. So you basically wasted a bunch of interaction effort without really increasing any of the performance. Even worse, sometimes, like a lot of times when we plot this graph, and especially when we do simulated humans, we also have this assumption that human is really patient. They have all the energy in the world and always will be able to engage in this kind of interaction. But realistically, like if you really frustrate people, if you lose people's trust, if you actually like instead of increasing the utility actually you got confused by the clarification or follow up from humans and the like output actually look worse, then this agent would have frustrated people and people would just give up altogether and drop out without giving more potential interaction and would like not be able to benefit the potential help from the agent if they were able to persist for a little longer. So if we think about all of these, to really build agents that would be supportive and helpful for like imperfect humans, We think evaluation should really capture two process dimensions. The first one is something we call stability. Basically, where is the plateau on the y-axis? Do model continuously provide more utilities with additional human involvement, assuming human is always going to give you more involvement and effort? And second one is the actual usability, how much human effort models can actually get before users would drop out. And these two dimensions together, we call it like collaborative effort scaling, which is an evaluation framework focusing on comparing the process of task completion, not just like where you end in the end. And how do you capture those dimensions? What do you actually measure in order to get that numbers? It's kind of pretty intuitive given the axes, basically two dimensions, one human effort and second utility. And both of them have many different possible definitions depending on the task and depending on the domain. For human effort, is it easy to digest information? Does it require human to really read really long text? Is it easy to assess correctness of the model output? Is it easy for human to give feedback, or can human only be able to say like, oh, something seems wrong? They cannot really pinpoint anything. And utility, is it making progress to a final goal? Is it offering knowledge per step? Is human even happy with this whole progress? Are all possible things that maybe like a researcher or like an agent builder would care about. And utility would incentivize human effort, and human effort hopefully should increase utility. So both would be interdependent instead of independent. And in reality, those are maybe high-level definitions or concepts of human effort and utility, but it's not impossible to measure those in actual interactions. And a lot of times it's really just can you interpret the log and a lot of the interaction data correctly? For example, for human effort, simplest thing we can measure is probably just number of interactions we had between the human and the agent. But we can also consider context length. How long are we asking human to read? What's the information density in that agent output? Does this output format or like the wording, the jargon it's using really match with the human expertise? Versus utility-wise, we can measure again output performance, or we can measure stepwise. Are there more information added compared to the previous round of information? And whether if human is asking a question, can you detect that's a question, and did you correctly answer that question? So it becomes like a stepwise question answering kind of task. In this very particular paper, we just did something that's, we used the simplest measurement possible to see like can we capture the different kind of collaboration process and also patterns. And we used simulation data from, again, collaborative gym on three different kind of agents and the same kind of task. So different agents powered by different models like Cloud, GPT-4, some of them prompted to just complete the task, some of them prompted to be collaborative and have more interactions with the model. And indeed, we observed expected patterns in our visionary framework. And also, we were able to really compare across AI agents and know like what kind of models or also prompts would be more helpful for what kind of tasks. So for example, here we saw that agents powered by some models have really better scaling. For example, Claude here on this figure on the right is really like basically we in these cases we prompted agents to interact with users to clarify to like ask questions, and this blue line with Claude you can see it started with really low utility that's like measured by output performance. That's because it was asking too many clarification questions without making any progress on the task. But once it knows what it's trying to do, is start to surpass any other models, and which means it can really better utilize the human utility, even though they started really low. But some models are really better off doing things on their own. And the screen line here is GPT-4 Turbo. It really surpassed any other model we tested at the time if you just have the agent complete the task on their own. But when you engage them in interactions, again, it started relatively low. And even when they reach their plateau time, it's still not even surfacing them just doing the task on their own, and it's not definitely not really matching what Claude is doing. So those models probably it's better for just completing tasks that would just require automation. And this helps with picking who would be your collaborator, who would be your task executor. So from this project, what are our answers of like how to think about the interaction process? Interaction process is really, we think, a trajectory between human effort and model utility. And utility, usually we should really be broadly defining them. So in tasks with evolving goals, for example, intermediate results can be even more valuable than a polished endpoint. And efforts also, a lot of times we want to minimize human effort, but if we want to increase utility in tasks that's evolving or where humans do not know the all the goals, we should really be more like well planning to the effort to sustain longer term gains with respect to scaling in order to increase utility. And the interaction is definitely not to be ignored. So what was this kind of evaluation? What can we do? We really want to use this framework to incentivize a lot of interventions we can do. So basically, just by looking this figure, it's a line chart with a lot of turns. And if you just look at this figure and calculate where turns happen, maybe we can do a lot of things. For example, we shouldn't ask humans more questions when utility already start to drop because you're going to have people input more effort without giving them immediate gains. Do not try to explore alternatives. Do more exploration when the current path doesn't seem to be working out, when the current user effort seems to be always just not increasing utility, or like do exploitation. Don't change what you're doing. Just continue doing the thing. If it seems like everything's on the right track, don't suddenly make random suggestions to people. This is also not like completely new. Even in 1994, there's a paper called Principles of Mixed Initiative User Interface that already describes this procedure of like trying to really calculate the utility of when to make an action based on the current task status. And one sentence I really liked from that paper, it's a lot of times cheaper to not to act than acting on a wrong goal. And encouraging users really would have its own value if it really helps bring longer term gain. So with this and with like the calculation that we do in this framework, we think it's really helpful to try to think about how we would operationalize the notion of user computationally so we can predict the goal, the utility, and also the cost of actions long term. And there are two ways that we try to operationalize this user computationally and try to do intervention. First, how to increase utility, and second, how to make more strategic use of efforts. And I will each give you one or two examples. But the first one of increasing utility, I want to talk about some work we do around user-centered AI instruction following. And one work I want to talk about is this paper called Checklists Are Better Than Reward Models for Aligning Language Models that we published in Europe's last year. So even though like most of the time utility like are widely defined, at least one like really commonly accepted form of utility right now is whether AI is following the user instruction, because this is kind of the default way of interacting with the model in all of the different cases, whether we want AI to write a story about dinosaur or like asking really serious questions with collective self-determination or do a lot of different kind of decision-making support from the model. Essentially, we engage in instruction following where we express what we want to do to the model so that model can help us achieve that. And if it can achieve it easily and with high quality, I think we would consider AI bringing in a lot of utility. But one question that confused us a little was what does instruction following actually mean? When users say something like, can you help me write a 150-ish word promotion text for like book The Great Gatsby? Essentially, human instruction are always just under-specified. What user actually mean might be a longer bullet point than what you can parse from that particular instruction. Some of them maybe are already easily guessable, like if possible, stay around 150 words is something already in the instruction. But then there are something that's maybe slightly harder to guess, but also are important. For example, because I'm writing a promotional text. The model should avoid major spoilers because if you tell me how the movie ends or how the book ends, it's not going to be promotional. It won't trigger more people to come and buy this book. And I didn't write this in the original instruction, but that's definitely going to be helpful to me. So user instructions are really imperfect representations of what users actually want. That's one kind of imperfectness of human. And as a result, if model really want to help people with that, model needs to do some guessing on the missing needs or on priorities across all of the needs. Maybe it's actually more important. It's usually probably more important for model to avoid major spoilers than staying exactly 150 words. If you're slightly longer, I'm probably okay with that. So one way to really make it more clean, make utility more measurable, and also increase utility is really try to explicate modular requirements, which we define as like any aspects of an instruction that, when absent, will cause a response to fail to some extent. With that definition, we want to train model to do better guessing by inferring requirements from failures. The intuition is we want to, given any instruction, we want to produce responses of varying quality from models of varying size and varying quality, and then prompt large models to write a checklist of all their possible failure modes and also produce weight so we know what are all the requirements that's not even in the original instruction. Give you another example. Say I want model to generate some quiz questions on AI agents with answers. If I just parse this out, I get some requirements. I want answers to be correct. I want each question to at least have an answer. I want maybe multiple questions, not just give me one question. But if I also see a bunch of other generations from the model, I would be able to get more failure cases. For example, if I see like one model generate a lot of questions that all start with what, like all of the questions are memory questions asking for a definition, then maybe I would be like, oh, I actually feel like as quiz, if we want to cover different learning objectives, so don't always give me what question, also give me, for example, application question, how to apply AI agent for this particular use case kind of question. And maybe in a different response, I see there are questions broadly about AI, who invented OpenAI, and the answer is not even correct. And that might also trigger me to check like are all the questions appropriately education and also are they all strictly about AI agents, not just AI in general? And key takeaway here is really criticizing candidate responses provides more coherent requirements that are not simply direct segments from the original prompt and can suggest failure modes that are not easy to anticipate a prior or like are not even intuitive to the user themselves. And this checklist empower agents or AIs to follow instructions better. So basically, we use all of these requirements that we collected and did a method that we call RLCF, RL on checklist feedback. Given each instruction, we generated the checklist I mentioned before synthetically, and also grade each response per checklist, and then combine the grades into a single weighted checklist score. And eventually, we use this score for RL, which specifically was TPO. And I did a bunch of experiments, and the key results that we thought was really interesting was first, RLCF really consistently outperformed a lot of other methods. That was also like promising. And more importantly, this guest from Arrow checklist really offered a lot more information and performed way better than directly just parsing requirements from the instruction. So high utility in instruction following can basically mean that models can fulfill requirements or checklist not too obvious from the plain instruction text. And that would be like a workaround of imperfectness. One more thing that I want to mention for instruction following, like when we talk about instruction following, a lot of times we're talking about large model. We're saying we want the model to do better instruction following. But at this point, most of the models eventually are powering agents or powering pipelines. So it's also important to consider what are instruction following, where are instruction failing at inference time, and what can we do about that. And for that, I want to also give a really small example that where we try to do still like some kind of more nuanced instruction flowing, but on like a RAG pipeline. And the paper is Beyond Relevance, Evaluate and Improve Retrievers on Perspective Awareness. And intuition here is again, user would give instructions, like you would want, maybe they want to write an essay opposing this claim that African government must implement tougher protections for animals. And if you want to actually write an essay, usually what agents or large models would do is first to retrieve some articles and then use some of the articles to ground the essay writing. But the problem is retrievers themselves do not really do instruction following very well. Retrievers would try to find the articles that are relevant. But because opposing is like a stance that only takes one word in a really long sentence of like require a really long sentence of instruction. Eventually, it's very likely that a lot of existing retrievers will basically rank um, an article that's relevant to this claim, but it's actually supporting this claim that our African government must implement blah, blah, blah. And as a result, if you use that to do the grounding, your model will give you like a perfectly written essay, well supported, but writing argument exactly from the wrong side. Um, and so here the bottleneck was really not the model cannot, large model GB 3.5 cannot do instruction following, but really like it's blocked by what retriever is giving to it. So what we did was we created a thing called perspective aware retriever, basically using some like embedding, augmentation, and regrounding to make sure that like the model will be able to realize opposing is a really important stance even at the retrieval step, and will be able to rank those articles the top so that you will have a final output result that's like satisfying to the particular original instruction that you have. So here, high utility instruction following also means making pipelines understand the priority by really amplifying easily ignorable user needs in the user commands, and especially for steps in that pipeline that like do not necessarily will be able to capture that nuance. And this kind of imperfectness was not because people didn't mention this in the instruction, but more like natural language is really unstructured. And if we decide this is the way we want to do interaction, we need to handle that as well. So really like user-centered AI instruction following, it's like a fancy word, but what I really mean is really a lot of times it's worth going beyond plain text and try to identify and weigh the true user needs. And then the other end of strategic use of effort, I also want to discuss some work that we do around like AI-centered human assessment and training. So first, a lot of times we can just do what we call institute intervention that already can save a lot of effort. In HCI, we have really long-standing research on like how AIs can take action based on the user behavior. And for example, like at this point, there are still a lot of work on user modeling and also how AI should take initiation. But we definitely benefit from models being able to model human way better. At this point, if you have like an AI agent that's monitoring your browser, if you highlight when you try to buy like a maybe a rack, and like when you look in the comment, if you search for cat or if you subconsciously just highlight maybe some sentences, say like durable to pet, maybe the agent will just be able to learn, oh, looks like you will have a cat at home and they can recommend more things to you that's relevant to cat or pets. And we're also doing some work in that sense. And some of the institute interventions that I think are interesting as some examples. So one thing we did was also something we mentioned before of like how do you measure X? One thing that define effort is really do you have the right expertise as humans to read what AI is generating. So one thing we did was in this paper called MOR, like better handling diverse queries with a mixture of sparse, dense, and human retrievers. We tried this idea of also just treating humans as a retriever. And as any retriever, we expect that human will make mistakes. And we basically treat this as a computational problem of saying like, can we measure like which particular retriever are less likely to make a mistake given a particular query based on how this retriever behaved on past queries. And with humans, basically, this can help us model this user human retriever's trustworthiness. Like if user have shown confusion in previous questions that's relevant, then at this point, maybe the model or the agent should decide not to consult humans on particular questions they're not familiar with, and instead consult external resources so that the human effort of answering clarification questions will be well put to questions that they can actually answer. Another example of in situ intervention. This is another problem that we run into a lot in interactions, which is over-reliance. Like model human would just blindly trust AI without really checking it. And at this point, really humans are spending less effort than what they should. And how can we try to increase their effort and make sure they check things and become the guardrail of models? And things we can do is really we can model a lot of times like the human attention. For example, we can track what the kind of click streams people might be having with the agent. If they do a lot of copy pasting between ChatGPT window and Google Doc without any time stopping to actually do any reading, then it's very likely that they're over relying compared to someone who like do a lot of precise editing before do any copy pasting. And that's when like maybe agent can say like, oh, can we stop here and encourage the model to do more. So there are a lot of things that can be done even just by tracking people's click streams, logs, and also some interaction patterns. But one thing we thought is really more important is like, especially because these days AI are deployed really broadly. Like it's very likely if you build any kind of scaffolds, it's not going to reach people who just want to use the native ChatGPT interface. So we were thinking like, can we, without helping people, giving them scaffolds, can we still make people be able to really spend less effort and benefit more from agents in the wild? And in that, we feel like long-term intervention is really important. And I also wanted to like come back to this work that I mentioned at the beginning of this talk, and really talk about the key contribution we wanted to make in that paper, which is to figure out what should users do to effectively make AIs work, and how should we really maybe change education even in order to make sure humans have the skill to really ask the right questions and do all the right things. So if you still remember, like what I discussed 40 minutes ago, I mentioned that in this work, after we have students do like data science course assignments with Gemini in Colab, we've collected a lot of the interaction data they had with Gemini in order to understand where they failed. But I think more importantly, we try to identify like not where they used AI, but also where they didn't use the AI. And this still comes back to this essential question we had. Like, because Gemini was basically built to be general purpose, and in Colab, it already had practically all the functionality you probably will need. Theoretically, AI should be able to help on any subtask that you can think about. If you were able to first identify this as a task AI you want to ask AI to do, and second, if the AI, like, if the task description was correct, if the instruction was correct. So we want to know where did students really miss the AI's help, where they could have get the AI's help to overcome something, but because of like not asking AI or not describing it correctly, they weren't able to do that. And also, how can we teach these students to actually overcome those like missed opportunities and actually benefit more from AI next time? So with that log that we collected, which was like a stepwise event with timestamps, what they were doing at very particular moments, we tried to do some semantic analysis, saying like, oh, for actions that are very like apparently coherent, pointing to the same kind of goal, we would group them together into episodes. Like here, students were trying to first get like data summary with some recommended plots built into Claude, and then say like, oh, enter the prompt, how can I clean my data set? With a bunch of these actions, we can infer that students' overall intent right now is seeking general guidance on data cleaning, blah, blah, blah. And here they did use AI, and we can detect like the user was stuck on how to approach data cleaning, and they used the AI to get conceptual guidance and other kind of help. And more importantly, here it's saying like AI was used to help overcome this challenge because students ask, how do I clean my data set? But there are also students who just get stuck and did nothing. And at that point, that's also becoming missed opportunity. We envision like what kind of AI usage you could have done in order to overcome that. And with a lot of that information analysis, we basically summarized a bunch of AI literacy that's really necessary across knowledge dimensions, including cognitive, like monitor when to delegate things to AI, conceptual, knowing like what the AI can do, what are some tasks that it can actually handle, procedural, like how to write clear instruction, how do you do task decomposition if things get over complex, and also are you just persistent enough to be able to do trial and error with AI when the AI cannot do your thing on your first try. So this is example of missing the couldn't fix the like key arrow problem. Like his first dispensationally student just failed to handle really complex explanation. And also conceptually, they didn't recognize that column name is not something in the context of this chat window of Gemini just because of how Colab was wired. So both of things are actually things you can teach. And for this case of like iterative visualization that I also showed you before, the student demonstrated basically doing everything right. Procedurally, they used really clear instructions and described their goals, like 5 years of pie charts. Conceptually, they recognize data information does not exist by default, so they copied a lot of the information over. And they were really persistent and also willing to iterate when the AI like I was doing something wrong. Like you did the opposite of what I asked. I would re-explain so you can do the right thing. And also metacognitively, they recognize that they can ask the AI for help if there's something that they didn't know. And all of these information really can help us design more targeted AI literacy training. For example, we had this other work that basically we designed like a whole training suite to help students better write instructions with really clear requirements, which is, if you remember, is like one thing that really like is an imperfectness in human, but we can improve that. And to do that, basically, we can just take in a lot of inspiration from software engineering training and have students replicate existing programs by like interacting with a very well-guarded large model that would recognize requirements implemented by the students. And this really helped novices better instruct large models. They can naturally use requirements in prompts even when they leave this environment of training, and they know they should not confuse AI by giving too much unnecessary info, and they should organize the prompt parts logically for easy revision. So really longer term and explicit interventions are really necessary, and they exist probably in the form of education related for future design. So AI-centered human assessment and training, I think what's really core here is on a balance of local decision, also global trajectory, and to achieve those through both short-term user modeling that brings in immediate gain and also probably longer-term training. So you probably noticed that I kind of named these two threads was like contrasting naming, like user-centered AI and then AI-centered human. This also kind of, I think, represent my thinking of the field. It's really feasible and probably valuable to try deeper integration of humans and AIs at this point, especially as like AI is becoming more and more advanced and actually getting more and more ready to really help people on complex tasks. And a lot of times, inference time could be really effective already, but training could be more fundamental and lasting on both the humans and the AI. But what to train and how to train is probably still open question. And also, how should we think of utility and effort together is another question that I always feel like we haven't started answering. Like right now, I just say utility-wise, you should do this, effort-wise, you should do this. But they have interactions, so a lot of times that part feels is still an explored domain. And this is a summary slide that basically wraps up everything that I talk about. If you hopefully like if you have one slide to take home, this would be the one slide. But with that, I'm happy to take questions.
That's
Thank you
good,
for
Sherry.
listening.
You, Sherry, for highlighting a critical gap in today's AI direction, like the assumption of perfect users. Your insights on novice users, unknowing unknowns, and the need for AI to support an interactive process are truly invaluable. Invaluable. Also, I'm also working on like AI in the education domain, and it
Mm.
sparked some ideas on how to align LMs more towards like student outcomes. And is there any question from the or on Zoom? And I have a question. So can this like novice user can be swapped into like a relatively small parameter language models? I don't know if you ever, I mean, I know there's like a use defined like two axes of
Yeah.
utility effort. I was thinking whether those can be actually used like some training, like a
Mm.
small language models, like
Yeah,
some.
yeah. Yeah, I think that's an interesting idea, and I think it's probably very possible. Like, if you're familiar with the paper, like the last year's iClear paper, like collab large model, that was for people who are not familiar. That was a paper that basically says we can train the model to be more proactive, basically by simulating, like after the first round of human request, simulating how the next one or two round of conversation would go and see what kind of clarification and additional requests the simulated user will be able to have and condense everything into like a single um, um, like AI output so that you can use reward model like reinforcement learning to train the model to say like I will proactively say what are the things that maybe are relevant. And that is I think also like one form of interaction that essentially is decreasing effort. I think that graph can be converted into a lot of different kind of interaction design depending on where we want to increase in terms of the like model utility. And it's possible that from that graph we can extract some scores to represent that. I think maybe one difficulty is really because effort and utility probably have different definitions in different tasks. How do you still like make sure you handle this like general purposeness of the larger model is maybe a question. Like if you define utility in learning domains as like how students are learning and define like in some other like information gathering domain as how much information you're gathering. Maybe your reward function is a little unstable because of the inconsistent definition. So I feel like that part probably need more study. But if we're saying this is the definition that across domain we should be using, I'm pretty sure it probably will help with learning.
Yeah, I'm trying to use on like I'm like the kind of next step is trying to simulate like a tutor student
Okay.
dialogue.
Yeah.
And yeah, I was thinking this might be some hints that I could use. But I'll definitely check out the page.
Yeah. Yeah, and I also have a student who is like working on education domain. So maybe I will have her also reach out and maybe you two can chat.
Thank you. And in the Slack, there's a one question. Can you share some thoughts on agentic RAG? Kind
Any
of broad.
particular
Yeah, I guess. Can you elaborate kind of? Um, mhm. Sorry, to read your first name. Event T.
yeah, any specific directions on like what dimension of agentic RAG?
Maybe I think since you mentioned like a human retriever kind
Mm.
of like introduced among like other retrievers, I think maybe that could be a specific question. Like, how can we, because I didn't like truly know about like what human retriever are
Yeah.
actually doing, but
Yes.
sounds makes sense.
Yeah. So in terms of retriever, I think at this point, like, um, yeah, the reason I wasn't sure about this question was like, is it making RAG agentic or like using retrieval as a tool for any agentic system? It feels like one of the two ways, but how it worked based on specific domains. So yeah, that particular, if it's talking about that like mixture of retriever work, that one basically was still like pretty much domain specific. And it was like a first attempt of trying to simulate user expertise. And that one we still have follow-up work going on. But the core idea of that paper was we have a lot of different retrievers, and different retrievers actually also have different assumptions of when they work the best. For sparse retrievers, for BM25, if you have keywords because they're trained on essentially keyword-based approaches, if you hit some jargons, those methods actually work the best. Versus dense retrievers, if you have vague questions, if you have maybe descriptive questions that won't hit a particular like scientific keyword, like those retrievers will work better. But because in reality, people will have both kind of search in the same domain. If they are stuck with one retriever, it's very unlikely for them to always benefit from that. So we wanted to say, can we pair their queries to the best kind of retriever that would handle that? And sometimes this also means you can ask maybe your advisor or like someone who is your peer, but you don't always want to ask them. It's very like how you would do like a decision between when you ask Google versus when you ask your peer for related work. But in that particular work, when we tried to simulate the retriever, it was basically there are some data sets that naturally would have questions across domains. So we try to simulate like if it's an expert in this domain, it's very likely they will answer question with way higher accuracy compared to like if I ask you to answer a question in physics, you might not be able to really answer that. So you would either say I don't know, or you would say oh it didn't, or like give a wrong answer or give a really shallow answer. And model will be able to capture that and use that as information. It's basically a distribution learning of what kind of characteristics really make a query really satisfiable to a particular kind of retriever, either a predefined or a human retriever. But it depends, like if you are a very stochastic human, like you know a little about every domain, but don't know much about that domain, and somehow like that might create some problem creating that particular modeling. But that's something we're still testing.
So thank you so much for your talk today. And let's give Sherry a round of applause.
Thank you all for coming and listening.
Thanks so much.